Okay, welcome to our video on basic differentiation rules and rates of change. The objectives we have in this video. Number one is to find the derivative of a function using the constant rule. Number two is find the derivative of a function using the power rule. The third one is find the derivative of a function using the constant multiple rule and or the sum and difference rules. Fourth one is find the derivative of the sine and cosine functions. And the fifth one is use derivatives to find the rates of change. So we have a lot, it looks like we have a lot to do, but luckily we've done some of this already. You did it in class on Thursday. Most of the differentiation rules that we have right now, I'm just going to kind of go through and we'll mention them, and you need to pause the video to make sure you write them down. The first one we have is what's called the constant rule. And really what that says is the derivative of a constant is 0. And so, in this situation, we know that if c is a real number, that the derivative of that c is equal to 0. In other words, if I was given a problem, if I was asked to find the derivative with respect to x of the number 7, that derivative is 0. Anytime you take the derivative of a constant, it is going to be 0. Now, why is that? Well, think of it this way. The constant function graphically is a horizontal line. We know the slope of a horizontal line is 0. We also know that one of the interpretations of the derivative is it is the slope. So therefore, since the horizontal line has a slope of 0, the derivative of the constant would be 0. The next rule we have is the power rule. In this case, this is the one we dealt with in class. You did a lot with it. And so what we have is if n is a rational number, so right now we're just dealing where the exponent, the power on x is going to be some sort of integer or a fraction, a nice fraction, then f of x equals x to the n is differentiable, and the derivative with respect to x of x to the n is n times x to the n minus 1. Right now, let's look at a couple of quick examples. The first one is the derivative with respect to x of x to the 7th. In this case, that one's right there. In this case, what we know is by the power rule, that derivative is going to equal 7 times x to the 7 minus 1, or I get 7 times x to the 6th. That would be the derivative of 7 of x to the 7th. In terms of the derivative for x to the 5/3, by the power rule, notice the exponent comes down, so I'm going to get that is equal to 5/3 x to the 5/3 minus 1, which if you do get the common denominator and subtract those, what you're going to find is that's going to be 5/3 x to the 2/3 power. So the derivative of x to the 5/3 is 5/3 x to the 2/3. The next one we have is the constant multiple rule. In this rule, it just says that if f is a differentiable function and c is a real number, any real number at all, then the derivative with respect to x of c times f of x is going to be c times the derivative of f of x, or if you prefer, c times f prime of x. Both notations are the same. Let's look at what this means. When we have, if I have a problem like 5, if I want to find the derivative with respect to x of 5 times x to the 3rd power. Well, in this case, I know that the derivative of x to the 3rd is 3x squared, so this is going to be 5 times the derivative of x cubed, which is 3x squared, which results in 15x squared. So therefore, the derivative of 5x cubed is just going to be 15x squared. Now we get to the sum and difference rules. In these rules, it says if f of x and g of x are both differentiable functions, then the derivative with respect to x of f of x plus or minus g of x is equal to f prime of x plus or minus g prime of x. So now let's look at an example of this situation. Let's say I want to find the derivative with respect to x of x to the 5th plus x to the 4th minus x squared. So in this case, what this rule says is that if I want to find the derivative of this thing involving these three terms here, all I need to do is take the derivative of each term and either add or subtract them. So in this case, that's going to equal the derivative I know of x to the fifth is going to be 5x to the fourth plus the derivative of x to the fourth, which will be 4x cubed, minus the derivative of x squared, which is going to be minus 2x. So the derivative of x to the fifth plus x to the fourth minus x squared is equal to 5x to the fourth plus 4x cubed minus 2x. Now it's your turn. What I want you to do is I want you to find f prime of x for each function. So in the first function, it's f of x is equal to negative 2x cubed plus 4x minus 1. The second function is f of x equals 8 times the fourth root of x. You might want to think about how that can be represented with an exponent. And the third function is f of x equals x to the 2/3 minus 3x to the 1/3. So what I'd like you to do is pause the video, identify the derivative of each one of those functions using the rules that we've talked about so far, and then come back and we'll go through the answers. Welcome back. Let's take a look at the very first problem. In that first problem, I have f of x is negative 2x cubed plus 4x minus 1. And so on that particular problem, if you take the derivative, when you took the derivative, you should have had f prime of x equal to negative 6x squared plus 4. In the next problem, you had 8 times the fourth root of x. What you really want to do is realize that that is equal to 8 times x to the 1/4 power. So using the power rule on this one and the constant multiple rule, I know f prime of x is going to be 8 times 1/4 x to the 1 minus 1/4 power, or I get that's equal to 8 times 1/4 is 2x to the negative 3/4 power. And that's fine. In the third problem, in this case, we have f of x equals x to the 2/3 minus 3x to the 1/3. And so f prime of x on this one is going to come out to be 2/3 x to the 2/3 minus 1 power minus 3 times 1/3 x to the 1/3 minus 1 power, which results in 2/3 x to the negative 1/3 minus 1 x to the negative 2/3 power. So there's the derivatives of those three problems. Hopefully, take a look back. If you didn't get those to match, take a look at what I have on there. And if you did get them to match, great job. Now let's take a look at the derivative of sine and cosine. In the packet that we did in class, I asked you to go and find the numerical derivative of both sine and cosine and take your best guess as to what those derivative graphs were. And a lot of you came up as you were looking at them, you told me what they were. So the derivative of sine of x is equal to cosine x. And the derivative of cosine x is actually equal to a negative sine x. So you have to be careful on that one. Usually people are fine with the derivative of sine x, but there's some sign mistakes, S-I-G-N mistakes, excuse me, that happen with the derivative when you take the derivative of a cosine function. Let's go through now and let's take a look at the proof of the derivative that sine x is equal to cosine x. The first thing I would like you to do is I want you to recall that from our sum to product formulas that we had last year in pre-calc, that the sine of u minus the sine of v, if I take the difference to the sine of two angles, that's going to be 2 times the cosine of the sum of the two angles divided by 2 times the sine of the difference of the two angles divided by 2. So what we have in this case is we want to find the derivative of sine of x. And I know by the definition of the derivative that we're familiar with that the derivative of sine of x is equal to the limit as delta x approaches 0 of sine of x plus delta x minus sine of x over delta x. So this piece right here is just the application, using the application of the definition of the derivative. Now, by the sum to product rule that we just talked about, I know that the numerator, this numerator up here, is going to be, will become, by the sum to product formula, will become 2 times the cosine of x plus delta x, remember that's the u in this case, plus x over 2 times the sine of x plus delta x minus x over 2. And this whole thing is still over delta x. When I simplify everything, this is now the limit as delta x goes to 0 of 2 times the cosine of 2x plus delta x over 2 times the sine of delta x over 2. This whole thing over delta x. So what I'd like you to do right now, pause the video, make sure you're comfortable with everything we have here, because we're going to pick on the next slide, we're going to pick up from this and go through and get to the derivative of the sine function. Okay, welcome back. Here we are. We'll see the conclusion of our proof for the derivative of sine of x. At this point in time, we now know that the derivative of sine of x is equal to the limit as delta x approaches 0 of 2 times cosine of 2x plus delta x over 2 sine of delta x over 2, the whole thing over delta x. Now here's where you have to go through and remember a little thing that we talked about last year, and you've seen a lot as you've gone through math. We always talk about that if you divide by a fraction, it's the same as multiplying by its reciprocal. So if I go through and divide by, for example, 1/2, it's the same as multiplying by 2. Well, the same idea goes in the other direction. In this case, the multiplication by 2 here is the same as multiplying the denominator by 1/2. And so by changing that up, I get that what we have here will become the limit as delta x approaches 0 of the cosine of 2x plus delta x over 2 sine of delta x over 2 over the delta x over 2. Take a moment, pause the video if necessary to make sure you are comfortable with how I went from this top line to this bottom line, or to the second line where I have in my denominator delta x over 2. Once you're comfortable, we'll move on. In this case, we know that this is going to be, and I'm just rewriting the problem now, this is going to be the limit as delta x approaches 0. I'm bringing that cosine of 2x plus delta x over 2 out in front of the fraction, and I'm leaving the sine of delta x over 2 over the delta x over 2. Now you might be sitting there saying, why did I do that? Well, I want you to take a look at this fraction here. That looks very similar to a special limit we dealt with before. When we had the limit as u approaches 0 of sine of u over u, that was equal to 1. So in this case right here, I know as delta x goes to 0, this fraction will go to 1. And so the limit as delta x approaches 0 in this case is going to be just the cosine of 2x over 2, because this delta x went to 0, times 1, which will equal, when I simplify it, the cosine of x. So therefore, the derivative of sine of x is equal to cosine x. The proof for the cosine derivative is very similar to this. If you would like to see it, we can go through it in class, or we can sit down during SRT or some other time and go through it. But otherwise, if you are comfortable with this and you are comfortable with just accepting that the cosine derivative will be very similar, that the derivative of cosine is negative sine, then we can move on. Now we get to rates of change. Now some of the things you have to realize here. When we talk about rates of change, number one, we're going to start out looking in terms of position. And the first thing you need to realize is that position is a function of time. Okay, that where I'm located, the position of an object is depending on the amount of time that the object has been in motion. And often what we use s of t to represent the position. Therefore, the change in position, which is delta s, is going to be s of t plus delta t, the amount of change in time, minus s of t. Next thing you want to know, you want to realize, a rate is always going to be a distance divided by time. For example, when we talk about the speed of a car at being like 70 miles per hour, that means that in that time, in 1 hour, I would travel 70 miles. So it's 70 miles as a distance over 1 hour for the time. Average velocity, this one is a change in position over the change in time, and we often use this as delta S over delta T. Change in position over the change in time. Just the standard notation that we're familiar with at this point. But this piece right here is going to lead us to something wonderful. We know that the velocity is equal to v, and that is going to be the limit as delta t approaches 0. I got to put that 0 in there, I forgot to. Of delta S over delta T, the change in position over change in time. Well, from what we knew before, the delta S, the change in position, is going to be S of T plus delta T minus S of T. So this velocity is equal to the limit as delta T approaches 0 of S of T plus delta T minus S of T over delta T. And you look at that, you say, wait a second, I've seen something like that before, and I'm telling you, you saw that when we dealt with the definition of derivative. And we know that this limit right here is just the derivative of the position, which we know as S prime of T. And therefore, what we get, and this is pretty cool, that the velocity function is equal to the derivative of the position function. Let's look at an example on this one. I know S of t is equal to negative 16t squared plus 85t plus 7. What I would like you to do is pause the video. I want you to find the velocity function by taking the derivative of S of t. And once you have that, I'd like you to find the velocity of this object when t equals 4. So pause the video, do those calculations, and once you're ready, come back and we'll finish this video up. One thing we do have to make clear on this one is based on this equation, the fact that I have a negative 16, that does tell me that I am measuring my position in feet. So in this case, what we know, you should have come up with the fact that the velocity function v is equal to negative 32t plus 85. That's the velocity function. And therefore, the velocity at t when t is equal to 4 will be v of t, v of 4, is going to be negative 32 times 4 plus 85, which in this case is negative 128 plus 85, which gives us a negative 43, and in this case we're negative 43 feet per second. So our velocity in this case is negative 43 feet per second. Now some people might be sitting there saying, well, wait a second, velocity is negative? Yeah, velocity can be negative. Keep in mind, velocity is different from speed in that velocity does give you a direction as well. So when we talk about velocity, there is a positive direction and negative direction. A lot of times for us, the velocity when it's going up is going to be positive, an object that's coming down would be negative. So in this case, after 4 seconds, using that position function, I know this object is going to be coming down and it's going to be traveling at a rate of 40, it's going to be coming down at 43 feet per second. So the velocity, that's why we came up with a negative 43 feet per second velocity. This now concludes our video on the rules for derivatives and the idea of the rate of change. Please review these, and in class we will spend some time working on those and preview of coming attractions. We will be going to work with the chain rule And well, actually, we're going to be going to the product and quotient rules first and then the chain rule next time. So hopefully you have had a good weekend, or you're getting ready to have a good weekend. And I will see all of you next class.